So now we will talk about decision trees because these are the trees that make up the random forest. So a decision tree is a supervised machine learning method that can be used for either classification or regression. And in this course, we're just using them for classification. So that will be the focus of the examples I'm about to show you. A decision tree will predict the value of the target by learning a simple set of decision rules from the training data. And we end up with a tree-like structure because these rules consist of a series of binary splits where at each point we ask a yes or no question, which splits the data into two subsets. So the model contains three different types of nodes: the root node, the internal nodes, and the leaf nodes. The root node is where we ask the first question that should be defined in such a way that it best separates data into two subsets that are as pure as possible. And pure in this context means that it is as close to having only one class in it as possible. Then we have the internal nodes where, again, we ask yes or no questions to divide the data into further subsets. And then at the end, we have the leaf nodes where we no longer divide the data into subsets, either because they have become completely pure or because we have reached some other stopping criterion. And then whichever class was the majority class in the data that made up the leaf node will be the output of the decision tree given the leaf node that we reached for a given set of observations. And so when building a decision tree, the first thing to do is to select which variable should be used as your root node. And we decide that based on the Gini impurity value, which is defined with this equation down here. And this equation tells us that the Gini impurity is defined as 1 minus the sum of the relative frequency of each class squared. And I have prepared a simple set of artificial data that I have created just for illustrative purposes. So in this fake data set, we have a total of 10 observations. 5 observations are of a cow with no mastitis, and the other 5 observations are of a cow with mastitis, or of cows with mastitis. And we want to use the decision tree to predict whether or not a given cow has mastitis based on the days in milk and the standardized forecast error of the milk yield that we got from a dynamic linear model, for example. And you will notice that in this example, the standardized forecast error of the milk is categorical. So they are either negative or positive. And I decided to do that just to illustrate how to handle categorical data. So in this case, a negative value for the standardized forecast errors of the milk yield means that the observed milk yield of the cow was less than the DLM had forecasted. And a positive value means that the observed milk yield was greater than the DLM had forecasted. And as I said, these are fake data, but they are based on the biological knowledge that a cow with mastitis will have a lower milk yield. And we also know that mastitis is a more frequent problem in the early stages of the lactation compared to later stages of the lactation. So when making a decision tree to predict whether or not a cow has mastitis based on these two variables, as I said, we first need to decide which of these two variables we will use for our root node. So We do that by trying to use each of them as a root node and see which one is best. So we can start, for example, by considering the standardized forecast error of the milk yield, where we ask the question, is this positive? And just to make it easier, we'll just sort the data based on this column. So we can now see that in the cases where this statement is true, we have a total of 4 observations. And in the cases where this statement is false, we have 6 observations. For the cases where this is true, we have a total of 3 cases without mastitis and 1 case with mastitis. So we can put that in this nice little table. And in the case where this is not true, we can see that we have 2 cases without mastitis and 4 cases with mastitis. So we can put that in the table over here. So these are our 2 nodes that result from this split. And now we will calculate their Gini impurities. So remember, the Gini impurity was 1 minus the relative frequency of each class squared, summed together. So the 0 class here in this node had 3 cases. We draw the 0 class 3 times out of the 4 times that, of the total of 4 observations that are in this node. So the relative frequency of the 0 class is 3 out of 4, and we square that. We see only 1 instance of the 1 class. So here the relative frequency is 1 out of 4, and again we square that. In the case where this is false, we have 2 instances of the 0 class, so the relative frequency here is 2 over 6, because there's a total of 6 cases where the milk yield was negative. And we have 4 cases of the 1 class, so the relative frequency here is 4 over 6. And remember to square them. And if we do the math, we can see that the Gini impurity of this node is 0.375, and the Gini impurity of this node is 0.444. Okay. Now we can use these values to calculate the total Gini impurity of this split. And we do that by calculating the weighted sum of both Gini values. And the Gini impurities will be weighted by the relative number of observations in each node. So this node had a total of 4 observations, and between the 2 we had a total of 6 observations. So the weight for this node will be 4 over 10, which we multiply by this Gini impurity. And similarly, the weight for this node over here was 6 over 10, because we had a total of 6 observations here, and we multiply this by this Gini impurity. And in total, that gives us a total Gini impurity of 0.4164. Okay, now we need to compare that to the total Gini impurity that we can get when using Dayton milk as our root node. But the first thing you'll notice here is that Dayton milk is not categorical, it is numerical. And the way to handle that is to first sort the data frame according to the Dayton milk from lowest to highest. And then we need to calculate the mean value between each set of two consecutive observations. So the mean value of 2 and 5 is 3.5, the mean value of 5 and 6 is 5.5, and so on. And now we have to try each of these as a splitting condition to see which one works best. So we can start by using this first mean as a splitting condition and asking the question, is the Daisen milk greater than or equal to 3.5? And we can see that there are 9 cases where this is true and only 1 case where this is not true. So, and among the 9 cases where this is true, we see the 0 class 5 times and the 1 class 4 times. And in the 1 case where this is not true, we see the 0 class 0 times and we see the 1 class 1 time. So here we have a node which only has 1 class represented. That means it is a pure node. And we can calculate the Gini impurity for both nodes as we did before, and notice that the pure node has a Gini impurity of 0, which will always be the case for a pure node. And now we can again calculate the total Gini impurity as the weighted sums, and we get a value of 0.494. And we can see that this is not better than the 0.4164 that we got for the standardized forecast errors of the yields. But remember, we are not done. We have to test each and every one of these as a splitting condition. And if you actually do that, you will find that this splitting condition down here gives us the best total Gini impurity. So we ask if Daisen milk is greater than or equal to 54.5. If we use that as our root node, we get a Gini impurity, total Gini impurity of 0.1668, which is less than 0.4164. And remember, we want the impurity to be as low as possible, so this is selected as our root node. Okay, so having selected this as our root node, that splits our data into 2 subsets. A subset where this is true and a subset where this is not true. And in the subset where this statement is true, we can see that we have 4 observations and all of them do not have mastitis. So we can see that this is a pure node. There's no need to split it any further, and the output from this leaf node, which it is now, will be the 0 class, and it could also be the output that there is an estimated 0% chance for mastitis. On the other hand, in the case where this statement is not true, we get this data set over here, which is not pure. You can see there's cases of both mastitis and non-mastitis. So now we can split this data set again, and again we can try to see how pure the subnodes will be if we used standardized forecast errors of milk yields or Daisen milk to split this data. And if you do that, you'll find that the standardized forecast errors of the yield is actually better in this case. So we can again ask the question, is the standardized forecast of the yield positive? If that is true, or in the case where that is true, we get just a single observation, where again, we do not see a mastitis case. So again, we have a pure node, which we can then make a leaf node with the output of the 0 class, or the output that there is a 0% chance that the cow will have mastitis. In the case where this is not true, we get this subset, which again is not a pure node. So we can either try splitting it again, or we can say that we have now reached some other stopping criterion, which we will say in this case. So that means that we again create a leaf node here, where the output will be the one class, so we believe that the cow does have mastitis, and the output can also be an estimated 80% chance for mastitis, because we see that 4 of the 5 observations here are mastitis positive cases, and 4 out of 5 is 80%. Okay, so that was a simple example of how to grow a tree. And you can, in principle, continue to grow the tree until you end up with entirely pure nodes. But you may not want to do that, because there's a great chance that many of those leaf nodes will contain just one or maybe very few observations. And that is when you run into problems with overfitting. And overfitting in machine learning just means that we have trained a model that works absolutely fantastically when applied to the training data, but it will be absolutely useless when applied to any other data. So it will be actually useless in practice. And there are some possible solutions to this issue. The first one is to set a minimum number of training inputs to be used in each leaf. So as an example, if we say that the minimum number should be 10, that means that if you are in a node where splitting it again would result in a leaf node that has less than 10 observations, then you don't do that split, and this node just becomes the leaf node, even if it is impure, and the output will just be the majority class of the node. The second option is to set a maximum depth of your tree. In other words, limit how many consecutive splits can be included in any part of your decision tree.